Welcome to part 3, in which we talk about linear and nonlinear transformations of data. Recall that this idea of a linear pattern in the data is very important for examining and understanding covariance and correlation because they capture linear patterns, linear relationships. And so it's very useful to talk about how to transform a data set through a linear and nonlinear transformation for numerical data. So first, let's think about linear transformations and really what it means to transform data. And why we might even want to transform data. Why might you kind of make these transformations? Well, we transform data, in essence, to because we want a linear pattern in our set of data. So if you look at Anscombe's quartet, sometimes we have nonlinearities or some kind of skewness in a set of data. And so sometimes we want to use transformations so that we can apply covariance and correlation. One way to think about transforming data, in the simplest way, is to look at a linear transformation of data. It's a simple way, and we like linear transformations because they don't fundamentally change the distribution of a numerical variable. All we're doing is we're shifting and rescaling the data. We see linear transformations used all the time, but we also see nonlinear transformations. And in a nonlinear transformation, the idea is to change the distribution of the data. We typically use nonlinear transformations when we have some sort of nonlinearity in the data, and we want to straighten out that nonlinearity or that skewness so that we can apply covariance and correlation. So let's look at linear transformations first. Shifting and rescaling data, what that means. So suppose we have some x variable, and we can index this x variable, the observations of this x variable, from 1 to n, where n is the total sample size. We can conduct a linear transformation of this x variable by multiplying x by some value, some weight, and then adding or subtracting some constant a. This is simply shifting and rescaling the data. B here, multiplying the vector x, or this sort of set of x observations, by b, that's going to change the scale of our x variable. And then a, is just going to shift the entire data set, really recenter it. We like linear transformations because this multiplying by b and adding a, it doesn't fundamentally change what's going on in x. It doesn't actually change the distribution of x. We're just shifting and rescaling x. We see linear transformations all the time. For example, if you want to go from feet to inches, right? So we're labeling x here as feet, and then y here as inches. So suppose you know that you have some metric that's 1 foot. Okay, you want to change 1 foot to inches? Well, in this case, you just multiply by 12, and you add 0, right? So you can think of, in this case, we're just rescaling the data by b here, and b is 12. And then we're not actually shifting around the data. If you want to move from dollars to cents, you have your x variable, dollars. If you have $1 and you want to change it to cents, you just multiply 1 by 100. And so we have this new variable y, just a linear transformation. All we're doing is we're rescaling this variable x by multiplying by 100. For both of these examples, we're not shifting around the data. There's no a is, in effect, 0. But you can think that there's still an a here. If we change, however, from Celsius to degrees Fahrenheit, this is a linear transformation in which we're rescaling the data by a weight, 9/5, and then we're adding this value of a equal to 32. All we're doing is, so if you have degrees Celsius, we rescale the data by multiplying this value for degrees Celsius by 9/5, and then we're recentering, or we're shifting around the data by adding 32. And 32 is no accident. 32 is simply the value at which water freezes. Right? In Celsius it's 0, in Fahrenheit it's 32. That's why we add 32 when we want to go from Celsius to Fahrenheit. Keep in mind, though, what's going on with this linear transformation. For each of these examples, we are not fundamentally changing what's going on. X and y, they're both either measures of length in terms of feet or inches, it's some sort of value of money for dollars and cents, or it's some kind of temperature. But we don't say that when you change degrees Celsius to degrees Fahrenheit, the number's different, right? The temperature has a different value, but the actual temperature, you go outside, the temperature is the same whether you measure it in degrees Celsius or degrees Fahrenheit. That's why we like linear transformations. They aren't fundamentally changing what's going on. We're just rescaling and shifting the data by multiplying and adding some value. Another example is to go from inches to centimeters. Here, if you have 1 inch, right, and you want to change that value to centimeters, you multiply 1 by 2.54, and you add 0. So in this case, b equals 2.54, a is 0, and that linear transformation will spit out centimeters. Right? We can also think of shifting and rescaling in a slightly different way by rearranging the terms. So we can linearly transform from y to x. In this case, all we do is we take our x variable and we want to go back to y, or if we want to go y back to x. It's just a slightly different way of rewriting what we just looked at. If you have a variable y, you can subtract out a and divide by b. Right? Again, this is just a different way of rewriting the equation. And again, we are not fundamentally changing what's going on. We're just changing the center and spread of the data, but not the shape of the distribution. So to put another way, you can think of b, when we're changing the scale, we're changing the spread of the data. And with a, we're changing the center. We're shifting the data around where that set of data is centered. So we can look at the same linear transformations using this slightly different way of rewriting it. So suppose we want to go from inches to feet. Okay, so you can just divide y by 12. Okay, so in this case, if you have 1 inch, if y equals 1, then 1 over 12, okay, will give you the feet. Okay, 1 inch is 1/12 of a foot. If you want to go from cents to dollars, okay, you use y divided by 100. So for example, if y equals 1, 1 divided by 100, that is 1/100th of a dollar. That's the definition of a cent. If you want to go from Fahrenheit back to Celsius, you can use this equation, which is, in essence, you're just taking y minus 32. So that's recentering, that's shifting around the data. And then you're multiplying by 5 over 9. Again, all that's doing is it's changing the spread, the scale of the data. And then if you want to go from centimeters to inches, back to inches, you can just take centimeters divided by 2.54, and that will give you inches. Again, all we're doing is we're doing these linear transformations. We're changing where the data are centered, and we're changing that spread. Okay. We like linear transformations because they don't fundamentally change what's going on with x. And there's one linear transformation that we see used often. That linear transformation is called a z-score. So suppose we have our original data, and that data is just some x variable with a set of observations. The z-score, or standard score, means the same thing. It's just linear transformation in which we take our values of x, we subtract out the mean of x, and we divide by the standard deviation of x. And that will give us what we call a z-score or standard score. So think about what's going on when we subtract the mean of x from x. Right? When you subtract the mean of x from x, we have a new mean. That mean is 0. Think of it this way. If a particular x value has a mean, as a value equal to the mean, then subtracting out the mean will give that x value a value of 0. So for example, if you have particular observations equal to 50, the mean happens to be 50, well 50 minus 50 is 0. So by subtracting the mean of x from each observation, we are recentering the data around 0. And then by dividing by the standard deviation, what we're doing is we're making it so the new standard deviation is 1, is in terms of units of 1. And so this value of a standardized score has a lot of great properties, and it allows us to compare really quite different variables. But again, keep in mind, a z-score, all it's doing is it's shifting and rescaling the data. To put it another way, it is simply recentering the data, and it's changing the spread of the data, but it's not fundamentally changing what's going on, the distribution of the data. So let's look at some of this going on. The other key point about the z-score I should mention is that by subtracting out the mean and dividing by the standard deviation, a z-score, it gives us the number of standard deviations of a raw score, either above or below the mean. So, and we'll look at that in just a moment. The other key point is that suppose you have a z-score and you want to go back to your original x variable. Well, you take the z-score, you multiply by the standard deviation of x, and then you add the mean back in. Again, all that is just going back to a different way of re-expressing a linear transformation. So we take our z-score, we change a scale, we change a spread of the data by multiplying by the standard deviation of x, and then we add that mean back in. So the z-scores, they have a mean of 0. You add that mean back in, we recenter back to the original data. All right. Again, this is just a linear transformation. We like it because even though we can change our x variable to z-scores, which have these nice properties of being centered on 0, having a standard deviation of 1, and then our z-scores can tell us whether a particular value is above or below the mean in terms of standard deviations. Fundamentally, we're not changing the data in terms of substantive interpretations. So one way we use these scores, or standard scores, is to compare different values. Right? So you can take any distribution, you can express all the values as z-scores, which are really distances from the mean. And we can do this no matter what scale or what mean these original variables are expressed in. Right? So this is, in essence, a very commonly used way of using z-scores. So here's an example. All right, suppose we have two students. One student is Megan, another student is Jasmine. And Megan, she has this test score, this ACT score of 26, and Jasmine has an SAT score of 900. Now, if you're not from the United States, these are two standardized tests. They're just basic tests, but they have different means, right, and different scales, different standard deviations. An ACT score is a college entrance test, and it's designed to measure how ready you are to attend college. Same thing with the SAT. And the SAT is usually taken on the east or west coast of the United States. The ACT is usually taken by people from the Midwest. The problem is that these tests have different means and different standard deviations. So it's difficult to know, did Megan do better or Jasmine do better in regards to these two sets of exam scores? Well, we know that the mean SAT score is 1,000 with a standard deviation of 100 points. And the mean ACT score is 22 with a standard deviation of 2 ACT points. So what we can do, since we know the mean and the standard deviation for both of these two variables, we can transform Megan's ACT score and Jasmine's SAT score into standard or z-scores. And then we can compare Megan and Jasmine on a similar metric, with respect to a mean of 0 in terms of standard deviations scaled with a standard deviation of 1. So let's calculate z-scores for both of these students. So Megan, we take her raw x value of 26, we subtract out the mean for ACT, and then we divide by the standard deviation of the SAT score. And then we get the z-score of +2. What that tells us is that Megan scored 2 standard deviations above the mean. That's what the z-score is telling us. That's why we like z-scores, because it's a very handy way of just instantly, she's above the mean. She did pretty well on the ACT test. If we look at Jasmine, we take her raw SAT score, her raw x value of 900, we subtract out the mean for SAT scores, which is 1,000, and then we divide by the standard deviation. All we're doing is we're changing the mean, so the mean now is 0, and then we're rescaling the values of SAT scores by dividing by the standard deviation. And then we find that she has a value of -1. This tells us that she scored 1 standard deviation below the mean. What this tells us is that Megan did relatively better than Jasmine. And we wouldn't know this by just looking at the raw scores. Megan's raw score is 26, Jasmine's raw score is 900. So just looking at the raw scores, you might think that Jasmine did leaps and bounds better than Megan. But that's misleading because Jasmine's score is based on a different distribution of data than Megan's score. And these different distributions have different standard deviations and different means. So what we can do with a standard score is put Megan and Jasmine on the same distribution, a distribution with a same mean of 0 and a same standard deviation of 1. So by doing this, it's very helpful to really know how Megan did versus Jasmine. We know that Megan did leaps and bounds better. And so with that, we will conclude our discussion for now of linear transformations of data in which we shift and rescale the data. Next, we will look at nonlinear transformations of data in which we are interested in taking some kind of nonlinear pattern in a set of data, some sort of upside down U or some sort of curve in a set of data. And we want to straighten out that pattern in the data so that we can use measures like covariance and correlation and other statistical models or measures of association that assume linearity.